Hey, what's up you guys? It's Ilarian Garbazo with you, and today we'll have a talk on supervised learning. Let's talk about it! Supervised learning is the machine learning task of learning a function that maps an input to an output based on example input-output pairs. It infers a function from labeled training data consisting of a set of training examples. In supervised learning, each example is a pair consisting of an input object, typically a vector, and a desired output value. A supervised learning algorithm analyzes the training data and produces an inferred function which can be used for mapping new examples. An optimal scenario will allow for the algorithm to correctly determine the class labels. For unseen instances, this requires the learning algorithm to generalize from the training data to unseen situations in a reasonable way. In order to solve a given problem of supervised learning, one has to perform the following steps. Number 1. Determine the type of training examples before doing anything else. The user should decide what kind of data is to be used as a training set. In the case of handwriting analysis, for example, this might be a single handwritten character, an entire handwritten word, or an entire line of handwriting. Number 2. Gather a training set. The training set needs to be representative of the real-world use of the function. Thus, a set of input objects is gathered and corresponding outputs are also gathered, either from human experts or from measurements. Number 3. Determine the input feature representation of the learned function. The accuracy of the learned function depends strongly on how the input object is represented. Typically, the input object is transformed into a feature vector, which contains a number of features that are descriptive of the object. The number of features should not be too large because of the curse of dimensionality, but should contain enough information to accurately predict the output. Number 4. Determine the structure of the learned function and corresponding learning algorithm. For example, the engineer may choose to use support vector machines or decision trees. Number 5. Complete the design. Run the learning algorithm on the gathered training set. Some supervised learning algorithms require the user to determine certain control parameters. These parameters may be adjusted by optimizing performance on a subset, called a validation set, of the training set or via cross-validation. Number 6. Evaluate the accuracy of the learned function. After parameter adjustment and learning, the performance of the resulting function should be measured on a test set that is separate from the training set. A wide range of supervised learning algorithms are available, each with its strengths and weaknesses. There is no single learning algorithm that works best on all supervised learning problems. There are 4 major issues to consider in supervised learning. Our first issue is the trade-off between bias and variance. Imagine that we have available several different, but equally good training datasets. A learning algorithm is biased for a particular input X if, when trained on each of these datasets, it is systematically incorrect when predicting the correct output for X. A learning algorithm has high variance for a particular input X if it predicts different output values when trained on different training sets. The prediction error of a learned classifier is related to the sum of the bias and the variance of the learning algorithm. Generally, there is a trade-off between bias and variance. A learning algorithm with low bias must be flexible so that it can fit the data well. But if the learning algorithm is too flexible, it will fit each training dataset differently and hence have high variance. A key aspect of many supervised learning methods is that they are able to adjust this trade-off between bias and variance. The second issue is the amount of training data available relative to the complexity of the true function, classifier or regression function. If the true function is simple, then an inflexible learning algorithm with high bias and low variance will be able to learn it from a small amount of data. But if the true function is highly complex, then the function will only be able to learn from a very large amount of training data, and using a flexible learning algorithm with low bias and high variance. A third issue is the dimensionality of the input space. If the input feature vectors have a very high dimension, the learning problem can be difficult, even if the true function only depends on a small number of those features. This is because the many extra dimensions can confuse the learning algorithm and cause it to have high variance. Hence, High input dimension typically requires tuning the classifier to have low variance and high bias. In practice, if the engineer can manually remove irrelevant features from the input data, this is likely to improve the accuracy of the learned function. In addition, there are many algorithms for feature selection that seek to identify the relevant features and discard the irrelevant one. This is an instance of the more general strategy of dimensionality reduction, which seeks to map the input data into a low-dimensional space prior to running the supervised learning algorithm. A fourth issue is the degree of noise in the desired output values. If the desired output values are often incorrect because of human error or sensor errors, then the learning algorithm should not attempt to find a function that exactly matches the training examples. Attempting to fit the data too carefully leads to overfitting. You can overfit even when there are no measurements errors. Stochastic noise. If the function you are trying to learn is too complex for your learning model. In such a situation, the part of the target function that cannot be modeled corrupts your training data. This phenomenon has been called deterministic noise. When either type of noise is present, it is better to go with a high bias, low variance estimator. In practice, there are several approaches to alleviate noise in the output values, such as early stopping to prevent overfitting, as well as detecting and removing the noisy training examples prior to training the supervised learning algorithm. There are several algorithms that identify noise training examples and removing the suspected noise. Training examples prior to training has decreased generalization error with statistical significance. Other factors to consider when choosing and applying a learning algorithm include the following. First is heterogeneity of the data. If the feature vectors include features of many different kinds, discrete ordered, counts, continuous values, some algorithms are easier to apply than others. The second one is redundancy in the data. If the input features contain redundant information, highly correlated features, some learning algorithms will perform poorly because of numerical instabilities. These problems can often be solved by imposing some form of regularization. Number 3. Presence of interactions and non-linearities. If each of the features make an independent contribution to the output, then algorithms based on linear functions and distance functions generally perform well. However, if there are complex interactions among features, then algorithms such as decision trees and neural networks work better because they are specifically designed to discover these interactions. When considering a new application, the engineer can compare multiple learning algorithms and experimentally determine which one works best on the problem at hand. Tuning the performance of a learning algorithm can be very time-consuming. Given fixed resources, it is often better to spend more time collecting additional training data and more informative features than it is to spend extra time tuning the learning algorithms. The most widely used learning algorithms are support vector machines, linear regression, logistic regression, naive Bayes, linear discriminant analysis, decision trees, k-nearest neighbor algorithm, neural networks, different multilayer perceptron, and similarity learning. Hey guys, give me your feedback, so push and press the like button and subscribe to my channel on data science. See you tomorrow!